Okay, this is for my Algebra 2 class, so a review before our half unit test for Unit 6. And I'm going to do a quick overview of what we've done, and then we're going to actually do problems from the review sheet, or at least most of the problems that would require some review. So the first thing we learned about was exponential functions, which look like this. Y equals, for example, 2 to the x. Okay, and later we learned inverse functions, so the inverse to that function, and we'll call this y2 because I don't want this to be the same function. They're two different y's, right? This would be log base 2 of x, okay? And very important property of inverse functions is that they are reflections of each other over this line, right? So if I graph them on the line y equals x. So if I graph them on the same grid, that's not good, let's do it this way. You will see that they are exact reflections over this line, like a mirror, right? Like a mirror. And let's make this dotted and small. Okay. So the anchor points are really important whenever we're graphing these functions. And of course, we're going to graph transformations. So these are called the parent functions, right? These are the parents of at least two of the ones we commonly use, log base 2 and 2 to the x. And the very, very important anchor points for any exponential function, that's the parent function, that is 0, 1. And then 1 and the base. So in our case, our base is 2. So 1, 2. If this was 3 to the x, it would be 1, 3. If this was e to the x, it would be 1e, which is about 2.7 something, right? And then, of course, don't forget the asymptote. So we have this horizontal asymptote. We call it an HA for short, right? And that's, of course, y equals 0 for the parent function, all right? And so this function here is going to hit these 2 points, and it goes up sharply. Actually, we can find the next point, which is easy. If we just plug in 2 for x, right? And we've talked about this many times. You can certainly always resort to a table of functions, a table of points, excuse me, to help yourself, right? And if we plug all these in, of course, this is 1/2, this is 1, this is 2, this is 4, and this is 8. So I can go to 2, 1, 2, 3, 4, and I can get a much more accurate look at this thing. I'm going to change colors just so I can see the difference. So my function basically asymptotes here. That means it comes really, really close but never quite hits it. And then it passes through this point, this point, this point, and any of the other points that we'd find, but it goes up sharply. And that's what an exponential function looks like. And if we were to change this to, for example, y equals e to the x, e is 2.7, right? Or y equals 3 to the x. All that does is it makes it a little lower here. It goes through the same very important point here, and then it goes up steeper, right? It goes up steeper. So 3 to the x would be steeper than e to the x. But they all basically do the same thing. They have the same domain. They have the same range. So let's take a look at logs now, right? So for logs, it's the mirror image. So this anchor point here reflects to here, right? So logs have this very important point. And for log base 2, which is the mirror of this purple one, y equals 2 to the x, that's our mirror point, 1-2. So it becomes 2-1, 2-1. And instead of a horizontal asymptote, of course, logs have this vertical asymptote. So this vertical asymptote, this VA of x equals 0, is the same for all parent log functions. That means no transformations. And this point is always the same for all of them. It's just this point that varies here. So this 1, 2 is for base 2. 1, 3 would be for base 3. 1, 10 would be for log, that's log base 10. And 1e, which is 2.7, would be for natural log of x. So natural log is the inverse. Okay, it's going to go something like this, right? And I'm roughing it here. These are the only 2 points that I absolutely graphed exactly. Okay, don't forget, by the way, so log base e to the x, we also use or instead, really, we use ln of x. So if you see this ln of x in the test, you can replace it with log base e of x. E is 2.7 something, right? And 2, so it's very similar to log base 2 of x. Of course, it has some unique properties, which we've talked about. So those are our two basic functions, and of course, they get transformed. So when we're doing problems, we will talk about the transformation from the parent function. But you have to know these two anchor points for the exponentials and these two anchor points for logs, and we've done that for a long time. You should know that by now. If you still need more help with that, of course, you can watch other videos on how to do that. Okay, we also want to make sure that we remember all our transformations from quadratics, from square root functions, from all kinds of other functions, because they all apply here for horizontal shifts, vertical shifts, reflection over the y-axis, and reflection over the x-axis. So I will go over those briefly when I'm doing the problems that cover those, but you should also have a good understanding of that before you go any further. Okay, so let's do some problems. Find the anchor points and sketch each of these graphs. All right, so let me actually steal one of these. And for some reason it's not letting me, so I won't steal one. Okay, so it's good. We should learn how to freehand it anyway, right? So, because I'm just sketching, I'm not trying to make a very accurate, 100% accurate, except there are two key points. Okay, so it's log base 2, so the parent function is this, right? Without the minus there, without the x minus 1, the parent function is log base 2 of x. It's actually right here, right? So let's graph that first, right? So if we graph that, we know all logs have to pass through this point, all parent functions, 1, 0, all parent logs. And of course it's base 2, so I'm also going to go through 2, 1. So that's an important point, okay? And I know it's got a VA right here, and I know basically what it looks like, so we could draw that too. I'll do that in black. So we'll go, roughly up here, and of course this way. That's pretty rough because I am using a hand digitizer here, so. Okay, there you go. So, and we can make a table too if we wanted to. We don't have to, but we can make a table. And you can get more values for better results, right? Okay. But what we're going to do is we're going to do this transformation over here. So we're going to do this, which is a reflection over the x-axis, and we do that at any time. The only time we want to be careful about anything is we don't want to do vertical shifts until the very end, until after we've reflected it, for example. So if you had a +1 problem like that, we want to be very careful. But here, it actually doesn't matter what order we do it in, but we are going to do the reflection first. So this is, whenever you have a negative here, that means y was negative a few seconds ago before we moved it over here. So that is a reflection over the x-axis, right? So that means so this dot here doesn't move, but this dot is going to reflect all the way down here. And these dots are going to reflect up here. So this one's going to reflect up here. And basically we're going to get a shape that looks like this, okay? So let me undo everything up until those points. Oh, actually, I don't want to do that. But I do want to get rid of this, okay? And this. And so what I'm going to do is I'm going to reflect this dot. So instead of 2, 1, it's going to be 2, -1, right? 2, -1. And I can just change that to be 2, -1. And that takes care of this, right? This reflection. Okay. But we also have another number going on here. We have this, and this is the same as parabolas, as is the reflection, and really all functions that we've dealt with up until now. That means a horizontal shift, because it's next to the x, it's right next to the x, a horizontal shift of 1 to the right. So that means all my x values are going to change by 1 to the right. So these dots here are going to move to the right. So this one is going to move to the right, as is this one. Now, okay. It's not going to work as well as I thought, but 1 to the right, and this, and then this one has to move 1 to the right. Okay, that's better. Now, notice, this does happen, right? My vertical asymptote did change. My VA is x equals 1, because when there's a horizontal shift on a log, it does change the vertical asymptote. In exponential functions, if there's a vertical shift, it will change the horizontal asymptote, okay? So the graph looks exactly like we had before. It's going to come very close to this dotted line, but not quite hit it. It's going to come through our anchor points right here and here. Of course, they've been transformed. And then it's going to slowly kind of level off, but not, of course, level off, but just turn this way. So that's good enough. That's it, really. And of course, if I give you graph paper in the test, it could be a little neater than this, right? The vertical line could be nice and straight. But these two key points are very important, okay? So 2, 0. And of course, these are not the same. These are not right anymore, right? Because I transformed them. I can't get rid of them. Let's see. But it's 2, 0, and 3, -1. So 2, 1, 2. This is 1. This is 2. 2, 0, and 3, -1 down here. These are my two new anchor points after my transformations. Okay, if there had been a a -1 here, then after everything we just did, we would simply drag each point down 1. So this would be 2, -1, and 3, -2. All right, wouldn't change the vertical asymptote though. We're going to ask you on the test for range and domain of this. I mean, we've done it many, many times. So just check back in your notes and your old worksheets for the range and domain. I mean, the big thing here is the domain is from 1 to infinity, not inclusive of 1, right? 1 to infinity in interval notation, not including 1. So we got to be really careful of that vertical asymptote. Okay, let's go to the next one. Find the anchor point to sketch. Okay, so this is an exponential function. It's base 2, so no big surprise. It's exactly what we've been doing. And we know what the parent function looks like, and we know what the anchor points of the parent function looks like. So the anchor points are, as always, 0, 1, and then whatever the base is, right? I got to label this 1. 0, 1, and of course 1, whatever the base is. In our case, that's 2. Okay, very simple. So the parent function looks like this. And then it goes up, and the horizontal asymptote is here. Okay, but a couple of things happen here, right? It shifted, so this is next to the x. Anytime it's next to the x, if the number is right next to the x, that's a horizontal shift, and it always works in the opposite as the sign here. So a +1 is really a shift to the left. Okay, so that means this point here, and if we made a table, we could see this, right? This point, which was 0, 1, got shifted to the left 1, so that's going to be -1, 1. But then immediately it's going to be shifted up 1. So everything is going to go left 1 and then up 1, right? Left 1 and up 1. So if I took this point 0, 1 and went left 1 and up 1, it'd be -1, 2. And if I took my other point here, which was 1, 2, long time ago, is going to become 0, 3, right? Left 1, up 1. Okay, so 0, 1, 2, 3. There it is. You can actually see it. And -1, 2, which would be right there. So if you saw the physical movement of this, if I go back and do that again, right? It used to be here, so I went left 1 and up 1. And there we go. Now, if I'm asking you for range, make sure you understand that it can't go below 1. So the range would be 1, infinity, not inclusive of 1. And the key anchor points are here. Y-intercept, of course, is one of the anchor points if they ask you that. And that's about it, right? This is no longer valid anymore because we transformed it. Okay. What are the horizontal asymptotes and y-intercept for the graph of this function, y equals 2 to the negative x plus 7? Okay, a negative next to the x means it reflects over the y, not over the x, right? Because it's next, it's not in front of the 2, that would be over the y. This is over the x, excuse me. This means over the y-axis. Okay, so our normal graph is, of course, the classic 0, 1, we just did it, and 1, 2, okay? But this negative here says, oops, you're going to reflect that over the y-axis. So this point doesn't budge, but this point, instead of being 1, 2, now becomes -1, 2 for this point, okay? So that means my graph's going to look something like this. Notice that the horizontal asymptote is still stated x equals 0, no change there, okay? But that's only this. All I did was this, right? Now, and I always said do the vertical last. Now I'm going to shift everything up 7. So that means every point goes up 7. So this point, which was 0, 1, goes up to 0, 7. And this point, which was -1, 2, goes -1, 9, I think. Let's make sure I'm right here. Goes up 7, okay? And this dotted line, which is where the border was, also goes up 7, right? So everything goes up 7. It's going to go way off the screen here. So I don't have to see it to know how to answer this question because that got shifted up 7. So that's my y-intercept. See, x is 0 here. So it's got to be one of these two. That's my only two choices that would be valid. And of course, it's y equals 7 because it went up 7. So the horizontal asymptote, they always just call it an asymptote here, but is y equals 7, because it used to be y equals 0, and it got shifted up 7. So choice A, pretty easy. Which function is best represented by this graph? Well, this looks like a regular log graph, right? Except for one thing, it has this point 1, 1. Normally, that point is 1, 0, as we've talked about many times. That's my anchor point. So somebody definitely moved my anchor point up 1. So without really looking at any other points, the only function here with a vertical shift of 1 is A. Okay, that's a vertical shift of -1. That means down 1. And these are horizontal shifts. A horizontal shift left and a horizontal shift right. We did not shift anything horizontally here. Because I can tell the asymptote is still here. My VA has not budged. So I know there's no horizontal asymptote. And there's a vertical shift. I can see that. And it's up by 1. I really don't have to check the other points. But of course, our other point 2, 1, our other anchor point 2, 1, which would normally be here, got shifted up 1 as well. So it makes perfect sense. Okay, which is represented by this graph. Okay, so this looks like an exponential function, but normally exponential functions go through here, and if it's base exponent of 2, right, if the base is 2, then I know the next point also would be 1, 2. So those are my normal points. Well, it looks like somebody took it and went right 1 and down 1, right? Right 1 and down 1. Same thing here, right 1 and down 1. So those 2 points, which normally would be there, got shifted to the right and down 1, and that's easy. These are down. These 2 possibilities are down. That means down 1. And also right 1. Well, right 1 is always the opposite sign, so this has to be B. And of course, you can throw it in Desmos and check your work and make sure that I'm right, because I do make mistakes when I'm rushing sometimes. Okay, which graph represents this? Well, this is a very standard parent log graph. However, what is the base here? It's actually log base 10. We don't see a 10. Right? We don't see a 10. So it's log base 10. Okay. But it's shifted to the left 3. Okay, well, my normal point is here, right? For any log function. And it was shifted left 3. So 1, 2, 3. So which one of these has a point at -2? Well, there's 2 of them. One of them is here, right? And one of them is here. The rest of these guys don't have anything at -2, so we can chuck that. But only one of these is a log graph in its normal position, which is this guy. This is a reflection, right? That's a reflection over the x-axis. That didn't happen. There's only one transformation here. It's left 3. So the answer is A. Okay, what's the inverse? Which function is the inverse of this function? Well, that's just log base 10. So it's just 10 to the x, right? Log base 10. There's a 10 hidden here. 10 to the x. If 3 log base 3 of 7 equals x, what's the value of x? Well, we know right away, this is crazy. Why would anybody write this? 3 log base 3 are 2 inverse functions. It's kind of like writing 4 squared square rooted. If you wrote 4 squared and then square rooted, we know the answer is 4. It's like it's undone. So this 3 to the x and this log base 3 are both inverses of each other. And so it's really kind of canceling itself out. So these are gone, really, and it's just 7 equals x. It's a very simple problem. What is the value of log square root of x? Okay, well, first of all, whenever I told you to evaluate, so what is the value? That's the same as evaluating. You always set it equal to something so we get an equation. So I'm just going to say x equals log radical 10, and we're going to solve this. Well, a couple of other things. We never leave square root symbols in these problems. We always change it to fractional exponents. And also the 10 is kind of hidden here. So I'm going to put log base 10, even though it's not required to be written. Okay, and this is to the 1/2 power. Why is this so important? Well, because 1/2 power can be put into the front of the log equation, right? Because that's a property of logs that very important. If you have log base anything of something, and that something is to a power of 2 or 3 or 1/2 or whatever, you can move the coefficient to the front. Okay, you can move this coefficient to the front, this exponent to the front as a coefficient, excuse me, and just rewrite the expression. Okay, and that's very important because this is easy. We've talked about this many times in class. You've had other problems on this. If you were to evaluate this, right, if we were to convert this to log form, and I can do that with the 1/2, but I really don't need to because this is so famous here, right? This is so famous that this would be 10 log base 10, just log base 10. Let me redo that. I didn't mean to write it like that. Okay, so this is really easy. It's just log base 10 of 10 equals x. We would 10 to the x both sides of the equation, so this would be 10 equals 10 to the x, and therefore x must be 1, right? Because there's a 1 there. So that's easy. Anytime you have a base of, or a log of something, and it's the same number, it's 1. So really, this is just 1/2, because it's 1/2 times 1, which is 1/2. So that's also a very easy problem. This guy, right? So log, we really haven't dealt with logs with variables for the base. So this is not really a true problem that we're going to have to deal with in the test, but the operation is pretty similar, which is we're going to 2x both sides of the equation to undo this log base 2x. So this operation of 2x to a power and log base 2x, this all kind of cancels out. We don't like to use that word normally, and you just get 80 equals 2x squared. So 80 equals 4x squared. Be careful, this is parentheses, right? So be real careful with that, okay? 2x times 2x is 4x squared. And then divide both sides by 4. So you get 20 equals x squared. Oops, sorry. Didn't mean to do that. 20 equals x squared. And then square both sides. So x equals square root of 20. Square root of 20 is square root of 4, square root of 5, which is 2 radical 5. We've done that many, many, many times in geometry. Okay, this guy, if all this is equal to x, what is the value of x? Okay, well, this, right, is really, see, I see a base of 3, and I see this, and I go, well, that is really 3 cubed, but flipped, right? Because 27 is 3 cubed, and it's flipped. So I'm going to really rewrite the problem as 4 log base 3 of 3 to the negative 3 equals x. And we got to be really careful how we write this, right? So this is log base 3 of this, and this thing's being powered by negative 3. And we just talked about that up here with the 1/2. The negative 3 is a power, so the power rule says if you have a log of anything to some number and that number is cubed or squared or negative 3 powered, you can move it to the front. And so negative 3 times 4 is 12. Just rewrite everything without the negative 3. I moved it to the front. That's a property of logs. If you're logging something and that something has a power to it, you can move the power to the coefficient of the log. And this is easy. We just talked about this, and we've talked about this many, many times. You have to just kind of know this. Log base anything of that same thing is equal to 1. So the final answer here is negative 12. X is just equal to negative 12 times 1. Okay, and that's D. Okay, this is a word problem. If the loudness of fizz in a can of soda pop is represented by this log function, where X is represented by the intensity of sound, how loud is the fizz? In other words, what is F when X is equal to 10 to the negative third? So this is just a plug-in problem, but it's utilizing our log properties, etc. So it's 4 log, big parentheses, 10 to the minus 3 is X over 10 to the minus 5. Now this looks really messy, but as we've talked about many times before, X to the 7th over X to the 5th is just what? X to the 7 minus 5, which is 2, right? 7 minus 5 is 2. Keep the base untouched. So 10 to the minus 3 divided by 10 to the minus 5 is just minus 3 minus minus 5, like 7 minus 5, right? X to the 7 minus 5. So this is just 10 to the negative 3 minus minus 5. Very careful, they're double negative. Minus 3 minus a minus 5, or plus 5, is 2. So really this whole thing in the parentheses just becomes 10 squared. And this is for log. Now notice there's no base. Why? Well, because no base means log 10. Really, I could have written a log 10 right here in the beginning of the problem, because anytime there's no log written, no base written, it's log 10. Okay? So F equals 4 times this. But this is a simple problem we've also done many, many times before, right? Right? So if I want to know what that is, if I wanted to set that equal to something like X, right? Which is how we evaluate logs, and I want to evaluate this. Okay, well, I could put a 2 in the front, so it's 2 log base 10 of 10. And why did I do that? Oh, because this is so important, because this is such an important identity. This is equal to 1. See, so it's just x equals 2. So this whole thing here, this whole thing, and I could have involved the 4, but it's just something that you recognize really quick, right? That this is the power of 10, so it's going to make it easy. This whole thing is really just equal to 2. Log base 10 of 10 is equal to 1. 2 times 1 is 2. So this is 2. This is 2. F is equal to 8 decibels. Okay, and that's B. And I think that's it. All right, so hopefully this was helpful to you guys. Of course, review all the other worksheets that we did, particularly the transformation worksheets, which we haven't done in a while, although I did 2 examples earlier in the video. Good luck, guys.